In the previous video, we talked about how Quicksort has a best case, which is theta n log n, and a worst case, which is theta n squared. In this video, we'll talk about, for an arbitrary input, just some totally random input, on average, Quicksort will take n log n time. Now, to do a truly rigorous analysis and proof of that fact, we would need to use some somewhat deep probability theory and a little calculus, but I'm not going to assume that you have the level of probability theory needed to go through the full proof. Instead, we're going to use a little bit of intuition and also some empirical analysis in order to hopefully convince you. But a full proof, I'll have to defer it to something like Tim Roughgarden's algorithms class, if you're curious. Okay, so let's talk about this first intuitive argument, which is what I'm going to call the 10% case. So let's suppose the pivot always ends up at least 10% from either edge. So it's not the best case, where it ends up directly in the middle, but it's not the worst case either, where you're right next to where you started. So in this case, maybe it ends up in exactly at the 10% mark, as bad as it could be given our assumptions. Okay. Now, given that fact, we end up with two subproblems, one of size n over 10, and the other of size 9n over 10. Now, when we do the partitions on these two sides, we'll see it's still in work. And in each of these two subproblems, we end up with, well, in this case, four subproblems. One of size n over 100, another of size 9n over 100, another of size 9n over 100, and finally one of 81n over 100. Okay, so we basically end up with four totally differently sized problems, and we still have that each level is n work. It's just some of them are a little bigger than others. Now here you might ask yourself, how much work is done at each level? And we'll say it's not exactly n. It's actually going to be, I'm going to be a little more general and say big O of n. Because eventually, if you keep doing this, the left branch of this tree is going to end. Well, eventually n over, 100,000 or something. It'll just be nothing. Whereas these big ones will take longer. So the tree will be a little skewed, in your perspective, a little skewed so that it gets longer on the right-hand side. But overall, we can upper bound the work at each level by big O of n. Okay. Now overall then, the runtime would just be that n times h, where h is the number of levels. And here, if we compute the number of levels, well, rather than it being a log base 2, it'll be a log base 10/9 for the example I have here. And so overall then, the runtime will be n log n, even if you're always 10% from the edge. And so the punchline here is that even if you're unlucky enough that you never land in the middle, you're always at around this 10% mark, but you're at least that lucky, well then the runtime is still big O of n log n. Now you can actually extend this same proof to say always ends up at least 1%, or 0.1%, or 0.001%. As long as it's some fixed percentage, then this proof still continues to hold. And hopefully that gives you some intuition for why, on average, you should be in pretty good shape. Pretty good shape. Now, approach number 2 is to make the observation that Quicksort is really BST sort. So this is kind of a whoa moment. This is something I did not fully appreciate till I taught this class probably 4 times. So it's a little tricky. I still haven't found the right explanation for it, but we'll try. So I'll take, for example, heap sort. So heap sort was you insert a bunch of stuff into a heap, delete it out, and you get the items in sorted order. You can imagine trying to come up with a sort which is, well, let's insert all of our items into a binary search tree. So I insert 5, then I insert 3, that's where it ends up. I insert 2, that's where it ends up. I insert 1, that's where 1 ends up. Okay, now comes 7. Okay, 7 is greater than 5, so it goes over here. 8 is greater than 5 and 7. Okay, how about 4? Well, 4 will end up in this spot. And then finally we have 6. So that would be BST sort. Now this is a tree, not an array, so to turn this into the sorted order, we would do an in-order traversal and get 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's BST sort. Now it turns out, but it is a little subtle, that this exact process we just did is Quicksort, and why? Okay, well, the key idea is to look at what the comparisons were that were made. So when we think about what comparisons got made so that 1 ended up in its position, well, it got compared against 5, then 3, then 2. Well, actually, in Quicksort, the same thing happened. When we partitioned on 5, 1 got compared against it. When 3 was partitioned, or was the pivot, we also compared 1 against it. And when we pivoted on 2, we also compared against 1. Okay, another example would be 6. So which partition operations involve 6? Well, it's when we partitioned on 5 and when we partitioned on 7. Same thing here. And so if you look at the compare to operations, like you just write them out on a piece of paper, which compares get called, you see that it's the exact same comparisons. So in some sense, they're the same thing, right? So if you just throw stuff into a BST randomly, you get Quicksort. And you may recall that random insertion into a BST in a totally random order, that should take n log n time on average. Now there's a study guide problem that you can check out to really prove this to yourself. I think it's a really, really neat point, a very deep connection, but a tricky one to really fully comprehend. So those are two intuitive arguments, but there's also the empirical argument. So in the empirical argument, what we can do is just generate a bunch of arrays, throw it at Quicksort, and then count the number of comparisons, whatever they may be. And so if you do this analysis, you can show empirically, this is a histogram, basically saying, okay, I generated an array, it took 12,000 compares, so I'll tick this bar up one notch. And so doing this over and over, we had a bunch of arrays of length 12, we had a bunch of arrays, all the same length, that took 12,000 compares to complete sorting, a few that took 14,000, a very small number that took 15,000, and so forth. And if you run this experiment over and over and over, you can compute the mean of this distribution and find it to be 2 in natural log n. In other words, the number of comparisons on average is theta n log n. And by the way, you can also compute the standard deviation. This is a theoretical result, but you can also show it empirically. It's around 0.648 times n. Okay. Now, if you, I guess to highlight the main points, like here, there are just tons and tons of arrays that if you generate random ones that take 12,000-ish compares to sort with Quicksort here where n is 1,000. Now, if we look at 15,000, there's only a very small number of arrays that take 15,000 compares. You got to get pretty unlucky to get there. Now, if we think about what n squared is, okay, well, 1,000 squared is 1,000,000. That's way over here. So the chance of taking 1,000,000-ish compares is effectively 0. So if you generate a random, totally random set of data and you feed it to Quicksort, it's basically never going to happen. You should be more worried about quantum teleporting out of an airplane and plunging to your death than you should be worried about this. So I think that's, I don't know, a pretty cool and convincing argument. But if you wanted to do it really, really, really for real, you'd have to turn to probability theory. So to summarize our performance, we got n log n in the best case, n squared in the worst case, and then totally random data, it's n log n with extremely high probability. Now, we need to think about corner cases, and I'll defer that to the next video, but hopefully I've convinced you here that on average, as long as we have random data, it should be n log n.